Welcome again to the finite element method for the engineering applications. Last week we have given an example, but we didn't finalize it. Before continue to the example, let me introduce you a little bit about the discrete systems and continuum equations. For our last week's example, we tried to look at the spring equations, and before that we again talked about the electrical systems and heat transfer and classical spring equations. Now I'm going to tell the differences between the discrete and continuous systems, considering the spring equations and Laplace equation. If we look at the figure on the left hand side, I'm talking about the discrete system. We have got a serial and parallel connected spring members and some masses to controlling the system. So we are trying to explain the equations by using F is equal to K multiplied by X, if you remember. And we call this one is a discrete system, and naming it like direct stiffness method. Today we try to talk about the direct stiffness method and using the spring equations for different examples. But if we are going to look at the more continuum forms in the right hand side, for example, we have got a flow of water here, and you can see a unit element on top of right hand side, and you also can understand the levels here. The left hand level is here, right hand level is here, and because of that, for balancing the system, water is going from here to here, and it's a kind of we can accept permeable soil. Water is transferring from this soil, and the level of the right hand side is going to increase, left hand side is going to decrease till to the balance system. We are explaining this one by using Laplace equation here that we have given. And for the numerical technique, you can see the approximation and continuum mechanics. For making it simpler and easier, we are using direct stiffness method. Let me come back and explain you the last week's example first. If I am going to put those equations again, we have got an one element example here. Yes, this one. We have given this to you. We have got a 30 pound per inches stiffness of the spring, and we have got a load of 30 pounds, 300 pounds per inch stiffness, and 30 pounds for the force, and one axial load on a one element. We can say something like that, and we can also show it like this, maybe here. We have got a one element, yes, and we have also a force applied from here, P force, and that is connected to the wall. And we have got only one axis, x-axis, that's it. And the stiffness of the material, which is K, is given here. Considering the initial equations that we have used for the basic definition, if you remember, F is equal to K multiplied by X. But if you look at the free body diagram, let me erase here. If you look at the free body diagram, we have got a reaction force on the opposite side. We can say something like that. And it should be equal to the minus P. Because of that, when we are creating the functions of the system, we are using one of it minus. And collecting those equations into one tensorial system, this one, we have used like one of it minus and the other one starting with minus, if you remember. So 300 U1 minus 300 U2 is equal to F1, and for the other one, minus 300 U1 plus 300 U2 is equal to F2. And this equation, as I told you before, it is a problematic system. Why? The determinant of this matrix is equal to 0 if you try to calculate it. And because of that, I have told you that we try to decrease the unknowns, or we have to add some knowledge to the system. Like here, U1 is a translational or displacement value. So I know that for the initial node, which is U1, and for the end node, U2, for the left-hand side, I have already know that this is connected to the wall, and deformation of the system, U1, and that is, we can say, like D1, should be equal to 0. So before solving the system, I have to make this one 0. And for the U2, I am adding the displacement value D2. And for the force vector, we don't know the value of F1. We try to solve for it. And F2 is the external given load, which is same direction with X. So because of that, we are taking that value plus 30, considering the 30-pound load. So let me explain you a few more things. I think you have tried to solve these equations. I hope you tried to solve these equations. If you don't, you won't understand what is going on for the next period that I'm going to explain to you. So let me start with here. Initially, we have to say that because of the determinant of this system is equal to 0, we have got no solution. we have got no solution. Why? Because here will be 0. So how are you going to find the displacement and force? It is not acceptable. So we have to make something new. We have to add something to the system to make it problem, to make the problem solution, or we need to get the solution by adding this one. So we need to eliminate some of the parts of the matrix system, of the tensorial definition. For example, if you look at the equations here, 300 minus 300, we will create an equation like 300 multiplied by 0 and minus 300 multiplied by d2 will be equal to f1. And I don't know f1. For the second one, minus 300 will multiply by 0 and 300 multiplied by d2, and it will be equal to 30. So starting with the known values, this one, I am going to eliminate the first row of the system because I don't want to find the f1 because the value is 0 already. I could not able to find it. So starting from the end row here, I want to eliminate this row. Because of that, I'm going to change the values to 300 to 1. Why? I will multiply it with 0. But considering this one, I will change the 0 to d1 again. So 1 minus 300, d2 and f1. I know that f1 has got a value, but I want to change it to 0 initially. Why? I need to find the displacement 2. Because of that, I am changing the equation. Let me show it to you. For example, I am changing the stiffness matrix to 1, 0, 0, and 300. So for the second displacement vector, d1, d2, and I will make it a new force vector with 0 and 30. Why we have done this? To change the matrix of the system and to clear, and that won't be anymore 0. I'm talking about the determination. So if you try to create the equations now, d1 multiplied by 1, 0 goes to d2, it should be equal to 0. Why? I don't want to solve for this one. I want to solve for the second one also, and just for it. So we will make the second row, first column also 0. Why? Because I want to eliminate the d1 also again. So 300 will be multiplied by d2 and it is equal to 30. So what we've got here? We got here the modification system, and we called this one is the elimination technique. So it is a kind of maybe you can use in different areas and learn something. So this is a little bit depends on your experience. Because of that, in the initial times it will be a little bit harder, but after a few examples you will start to learn how we're gonna make it. So we need to eliminate the system. The first row, sometimes or rarely we say we can use here 0, but generally in the first row, first column, we accept 1. But for the second, third, fourth, if we have, we will make all of them 0. And for the first column also, we will make all of them 0 if we have. We eliminated the unknown definitions. So we just try to solve for the D2 for this definition. 0, D1, 300. D2 will be equal to 30. So we call this elimination technique. And we are imposing now essential boundary conditions. Don't forget it. Essential boundary conditions. We will explain it in the future in detail. And when you change this one, this equation, so you will get do you understand? After this one, we have got 300 D2 is equal to 30, so we will have a value of 0.1. So the length of the system is explained by inches, so we have 0.1 inches. In terms of vectoral definition, I can write it D1, D2 is going to be 0. That I have already know it. It is 0 because it's connected to the wall. So this one will be 0.1 inches. And for the secondary unknowns, this one, first unknowns, displacement. Secondary unknowns, forces. I have written here 0, but I know that it is not. I just did it for solving the primary unknowns. So let me change it to the real value, put the original value back here. Let me change it. I can write it like 300 minus 300 minus 300 again 300, or you can write it something like that. That is the same in this way, or this one is easier. 1 minus 1 minus 1, 1, 2 times 2 for the row and columns of the matrix, D1, D2. Also, I can continue here. D1, D2, and that is equal to, I have give this value 0, I know it, I have found this value 0.1, and it will be equal to, and if you find here 30 and the values are equal, you can find it F1 is also for the balancing 30. So I can write it, but because the F1 will be the opposite direction of P, you should write it minus 30. 30 in terms of pounds. This is very simple definition. So let me draw the spring system. Minus 30. We have got the node 1, first element, spring definition. Second node, the nodal load 30 for the first node. Second node, we have got the stiffness of it, and the direction will be on X. This is a very simple definition of this system. Let me explain a little bit basics of this approximation and continue a few more examples to make it clear in your mind. Because of that, I want to explain you a little bit about the matrix and linear algebra, let me tell you. So matrix algebra, you have to remember what we have been using. Let me give you a few steps for you so you can remember. But if you don't remember, you have to study, because our whole job is about the linear algebraic equations initially. So if we have got this kind of equations, polynomials, so a11, x1, a12, x2, it's just going like a1 and xn is equal to b1, b2, bn. We need to make all of these equations into one, so we have to write them into a matrix form. Because of that, I will write it like ax is equal to b. In terms of matrix system, I will write something like that. This one. If A matrix can be displayed here, A11, A12, it is going to till A1n. And for the columns A21, it is going to AN1. And finally, to the last column and the last row, ANN. So I will explain it like n times n. You can understand this one initially will be for the stiffness and for the x and b. X is going to be a kind of displacement vector, and b can be said like force vector. x1, x2, it is going to xn. B vector is b1, and going to be n. So n times n, that is very important, this one, which is going to tell us a square matrix. It should be square matrix. And x and b are column vectors of the dimension n. So for the row and column vectors, we can write something like that again. For example, let me write it to you. For the row, v1, v2, etc. And for the column, let me use omega 1, omega 2. We can write this one is row vector and this one is column vector. You have to remember the matrix addition, subtraction, and scalar multiplication, etc., etc. Those are the basics of the matrix system. If I want to tell the transpose of a matrix, what you understand from that, I will take this value here, this one here, this one here, this one here. So I will make the first row here and put it here as a column. So it will be A11, A12, A1n. And for the second one, A21, A22, it is going to A2n. So this is the transpose of the matrix A. For the unit matrix, let me clear here. For the unit matrix, it will be I is equal to 1, 0, continue, and it is going to 0. 0, 1, 0. It will be 0, 0, and here should be 1. So we have to know that this is called identity matrix or unit matrix. We can say that A multiplied by unit matrix should be equal to again A. And for the scalar again, if you change the direction, it is X. So you have to remember how is the determinant of the matrix will be calculated. You have to study for it. Maybe I should tell you about a singular matrix, which is important in the finite element method. Singular matrix, for example, I can tell you that a square matrix A is a singular if the determinant of A is equal to 0, which indicates the problems in the systems, non-unique solutions, degeneracy, or etc. So you can understand that if the determinant of the matrix is 0, which we faced initially in our example, it is called a singular matrix. You understand? Or matrix inversion, maybe we will use it in the future. A matrix of A will be multiplied by inverse of A. So I can write something like that, inverse of A multiplied by A, which is equal to identity matrix. So we can write something like that. Inverse of matrix A can be defined like 1 over determinant A multiplied by constant transpose matrix. So I'm going to explain it like in parentheses, matrix A and B, inverse of them is equal to B inverse multiplied by A inverse matrix. So there are a few more things that we should know about it. For example, we have got many methods to solve these equations, but we generally use the Gauss elimination methods to find out the unknowns for the matrix system. You can use also iterative methods. Sometimes it's good enough, but sometimes it won't. For example, one more issue that you should know, what the positive definite matrix is. We can tell that a square n times n matrix, like, let me write it, we have got a square yes, and the definition is n times n. If this is square matrix A, we can say that it is positive definite. So, if for any non-zero vector, x of dimension n, so I am able to write it like x to the power t, which means transpose of the matrix A should be multiplied by matrix X, I'm sorry, so it is going to multiply by AX, which will be bigger than 0. So we can say positive definite matrices are non-singular. Because we said that for the singular matrix, a square matrix, if the determinant A is equal to 0. So this one, if you see, it is bigger than 0. So it is positive definite, but non-singular. So let me finalize this little glimpse of linear algebraic equation definitions. A short definition and short briefing to make it clear for you to understand the equations, and starting to explain spring element more detail. Let me give you, if we have a spring definition like this, we will have got a node of I and the other node and node J. We have got a force Fi, we have got a other force Fj. For the axis, we have x-axis, and the deformation or translational values uy, uj, and the stiffness is k. We have got nodal displacements. These are nodal displacements. So these are nodal forces. And we have got spring constant, or we called stiffness, which we explained it before, like the material definition. So this is stiffness. We can say that the units can be pound per inches or Newton per meters or Newton per millimeters, etc. So we have got a graph. I'm talking about force and displacement graph. You can convert it into stress-strain graph after this one. So we have got an elastic value, and here you have got a K stiffness. If this one going like this, it is linear. If this one going like this, it is non-linear. So you can write it F is equal to K multiplied by delta. If it is bigger than 0, the force needed to produce a unit stretch. So we have written these equations. I'm going to write it again. Fi is equal to minus F, which is a reaction force, can be written like minus K Uj minus Ui is equal to K Ui minus K Uj, and for the node G, Fg, this time it is positive. You will write it K Uj minus Ui. But for creating the matrix system, you have to take the Ui to the start, and you have to take the Uj to the end, because in the matrix system you are going to write U1, U2, U3 again for the second row, the same order, 1, 2, 3, 1, 2, 3. So it will be IJK, IJK, etc. So the Ui will be the first element. Because of that, you are changing the order. So it is created minus K Ui plus K Uj. So in the matrix form, we have already written like K minus K minus K, K, and the nodal displacement vectors Ui, Uj. Sometimes people are using D in terms of displacement. It is equal to force vector Fi, Fj. So this is defined like K multiplied by U is equal to F. Element stiffness matrix, element nodal displacement vector, element nodal force vector. Note that K is this one is a symmetric but singular or non-singular. We can say both of them, but if you remember, if the determinant is equal to 0, it is singular. But we have to write an elimination technique to solve for it. So, I want to give you a two-spring system. Let me write it, or let me find you a definition for it. Yes. This one. We have two springs connected serial, and considering the x-axis, we have got two elements, and because of that, three nodes: node 1, node 2, and node 3. Three nodes, two elements, and we have got two stiffness values, K1, K2, and we are applying, or we have F1, F2, and F3. Initially, we are able to write definition system separately. Let me write it for you. I'm going to write it for element 1. This is element 1. Some of the people writing, for example, elements can be in a square form, nodes in a circular form, to not create a complex or problematic scheme. So let me write it. We have got K1, 1, minus 1, minus 1, 1. And translational vector U1, U2. And for the forces, we have got first part, there is only one force in the element 1, but inlet of that force, 1, 1, and outlet of that force, 1, 2. First element, first force, first element, second force. And for the second element, I will write it in the same manner. K2, same thing, 1, minus 1, minus 1, 1. This time, it is going to start with U2 and finalize with U3 is equal to, this time we are in the second element. Now it is second element, first force, second element, second force, and force vector. This is going to tell where Fmi, like how many forces we have, so you can say that M element number, and we have got I, so I can be 1 or 2, like this type of applications, because one of it is inlet, one of it is outlet. So for this one, I can write like this type of explanation. I can say that F1 is equal to F11 and F2 here. We have got F1. We have got here F2. But for the inlet F11, for the outlet F12. For the F2, for the inlet F21, for the outlet F22. Because of that, I can write F2 is equal to F12 plus F21. And for the node 3, I can say that F3 is equal to F22. Considering this, let me write the equations, all of them. Maybe I should take this. Here. Let me write the equations. We have got F1 K1 U1 minus K1 U2. For the F2, we have got two values. So let me write all of them together. Minus K1 U1. And for the U2, look at here. U2, you have got two values. Which one is the K1 is coming from here. K2 is coming from here behind. So I will write it plus K1 plus K2 this is for U2, and we have got also minus K2 U3. So for the F3, you will have minus K2 and it is U2 plus K2 U3. Now I'm going to create an assembly and I'm going to take all of the systems, two separate systems, into one tensorial definition. So I am able to write this time K1 minus K1, and we have got U1, U2, U3, right? So for the U1, for the U2, for U3, there is nothing with, think about the node 1, there is no connection with node 3. There is only connection with node 2 with the help of K1. So this should be 0. For the node 2, there is a connection with node 1 with K1, and there is a connection with node 3 with K2. Because of that, I am able to write minus K1. So for the second, because of two connections, K1 plus K2. For the third node, we have got only K2 minus K2. For the third, there is no connection with node 1. I'm talking about the node 3. So here should be minus K2. Here will be the K2, which is going to multiply by nodal displacement vectors U1, U2, U3, and that will be equal to F1 F2 and F3. This is an assembly form, and we can write this time in capital letters. K multiply U is equal to F. K is the stiffness matrix, this time not a element. This time K is the stiffness for this structure. It is this structure matrix, this one, for the spring system. And now if I am going to write in a assembly mode but not use the second element or the first element, how I am going to change the system? Let me change this. Let me erase here. And write the, or take this one for a simple way. Maybe all of them. Yeah. If I'm going to take all of them and change it. Yes, let me change it. Now, if we make it simpler, we will write, instead of those, 0, 0, and 0. But if we write those 0, I will again change here. And maybe we will erase here also. Write the internal force definitions. We have F11 here. We have F12, and there is no connection with node 3. For the other part, I want to erase here. Yeah. I will get the copy again, so I will write the other definition. This time I will change it, so I won't use the K ones. Let me write 0 instead of them. And change here also. Like this one, this time the third node. There is no connection with the first one. Because of that, I will write 0. For the second element, first force, second element, second force. And this is an enlarging the stiffness matrix for elements 1 and 2. And we can write in this form. So, I will clear here. In the beginning, you will write these equations. And if you don't understand or you have got a difficulty to write this one, the assembly mode initially, You can write this one separately and create the connection here. Look at here. Because you have got a positive K1 and positive K2, in the second row, second column, you are adding them together. Why? In the second node, you have got a connection with K1 and K2. Because of that, the stiffness values will be added. You have got this summation of that value. So let me continue. If we write this one, or I can change these values just. You can write also something like that. We have got the force, first element, first force. For the U2, we have got first element, second force plus second element, first force. And for the node 3, you have got second element, second force. So this is the same equation using the equilibrium behind. So if we add the boundary and loading conditions, we already know that we assume this one is on the wall. It means U1 is equal to 0 for the elimination technique. And we have got a force of P for creating the tensile load. We accept them. P is equal to P. So I can write that time F2 is equal to F3 because there is no internal force, we said. If we have, it won't be equal. This time it's equal. So I can write something like that. Let me take this one. Here. Instead of these force definitions, let me clear it again. And I'm going to write the values, which will be F1, and this time PP. And we have got the stiffness values, and instead of U1, I'm going to erase it, delete it, yes, and I will say it is 0. So if I want to reduce the system to the U2 and U3 form, which is equal to, so I can say that I am making these 0 and this one 1. Not to show that, I will accept just here. Just here. I'm not using the other part. Because of that, let me write it. I can say K1 plus K2. If I was saying that this column also is going out, so maybe I should show something like that. That will be much more easier to see. Okay, K1 plus K2 minus K2 minus K2 and K2. It is multiplied with U2, U3, and it is equal to PP. And we can also say that F1 is equal to minus K1 multiplied by U2. If you solve this equation, you can see something like that. And the unknowns, if F1 is desired, so we can say that U2, U3, after the elimination, you will have 2p over K1. You need to solve this equation, guys. You have got K1 plus K2 multiplied by U2 minus K2 U3 is equal to P. And the other way, two unknowns, two equations. So you will solve these equations, find these values. 2P over K1 plus P over K2. After this, you will get F1 is equal to minus 2P. So, from the statics, if this is P, so there is only one more P, it means you have got 2P, and the direction will be other. It is statically also equal. You can validate it. And now, let me continue with three linear spring system now. This time I have these screenshots, so we have much more easier definition. We have got a three spring system, but the beginning of node 1 and the end node for node 4, we will have a connection with the wall. We can say something like that. Because of that, I'm going to give you the values. Yes, let me give you a snapshot again. I have got the values of the system. Yes, K1 is 100 Newton per millimeters, K2 200, K3 is equal to K1. And we have got a external load of P is equal to 500 newtons, which is applied at the third node. And we have already knew that the nodal translation of 1 and 4th nodes will be 0, which are connected to the wall directly. So, the purpose of this example, we have to write the global stiffness matrix, assembly of the matrix. So displacements of the nodes of 2 and 3 and the reaction forces at node 1 and 4. Finally, we have to know the force in the spring 2. So, if we want to write these stiffness matrices separately, how are we going to write it? For the K1, 100, let me write one of it. 100 minus 100 minus 100 and 100. This is the stiffness, Newton per millimeter. For the second one, K2, 200 minus 200 minus 200 and 200. For the third one, it is again this. It is equal. If I am going to write all of them together, so you need to combine them. So there is a connection point in the second node and also in the third node. So let me write the matrix. So you have got K1, K2, K3, which means we will have 4 times 4 stiffness matrix, if you understand. You have got 100, and then for the second one, minus 100, right? Is there any connection with the second or third element, or third or fourth node with the node 1? No. For the node 3, 0. For the node 4, 0 again. If I'm going to continue, minus 0 and minus 100, sorry. This time, 100 is coming from here. And there is also 200 coming from here. So again, it is positive. 100 plus 200. And for the third, there is a connection, which is going to be minus 200. And there is no connection with the node 4. That will be 0 again. This time, we are going to the third node. Let me write something like that. U1, U2, U3, and U4. This time there is no connection with this, 0 because of that. So I'm going to write the third. It is going to start with again what? Minus 200. Minus 200. And this will be 200, but this time we are writing for node 3, and there is a connection with node 4, with the element 3. So I need to write it like 200, and this time the stiffness of K3 is going to add here. So I will add 100, and again the end part of it will be just for 100, and it should be negative, minus 100. There is no connection with first element, there is no connection with second node, and we will write minus 100 and 100 here. This is the global stiffness matrix for our 3 serial connected spring and 1 internal force at the third node. After that, you will write the latest form like 100, or instead of writing, let me reduce the time. I will write the total value. Second row, second column 300, and here again third row, third column will be 300. And we call this type of matrix symmetric matrix. Look at the values. If I'm going to draw the orthogonal system, so you will get these values, one here, one here, one here, one here, and look at the zeros and the values. We call this type of matrix symmetric matrix, and you can also write something like that. Instead of writing these ones, you can write just something like that, symmetric. And because we have a band here, we call symmetric and banded matrix. The values on the band here. So now let me change this into the real tensorial definition. Let me write 100 minus 100, 0, 0, minus 100, 300, minus 200, 0, 0, minus 200, 300, minus 100, 0, 0, and to define nodal deformations, you will write U1, U2, U3, U4, and we will have again, we have an F1. This time we will add that value at the third. We already know that it is P force, P, with the value of it P. I know that F1, F4, they are the reactions. So because of that, to eliminate the values, I can say that this value will be 0. Just for now, because of creating the solutions. And I have already know that U1 will be 0, U4 will be 0. So I am able to eliminate the first and fourth rows now. Why? Because this time we have got a knowledge at the center. And because of that, I am making this value 0. Why? I'm going to eliminate one of the value. I will find one of the displacement. I will make these ones 0. I will use the second row and third rows and columns. So the basic approximation area will be here now. Why? Because these one is belong to F1. I don't want to find F1. Why? Because I have already know U1 is 0. I don't want to find F1 because of that. And I don't know the value F1 also initially. You can say from the statics equations, but you don't know, or the computer doesn't have any idea about it. It is your mechanics knowledge. And for the fourth row again, so for the first one, it will be going to multiply with this one. Because of that, I don't need that value. This one is 0. This one is going out. For the last value, it is 0. It is going to multiply by U4. It is 0. I don't need to find it. And it's going to equal to the F4. I don't want to use it also. Because of that, accepting those areas, let me write the elimination system. 300 minus 200 minus 200, 300, and we have a displacement vector of u2, u3 that is equal to 0 and p. And if you solve this one, again, two unknown and two equations, we have already know the value of p. So you will have a solution u2, u3 is equal to p over 250 and 3p over 500. And we can finally say that it is 2 and 3. U2 is equal to 2 millimeters, U3 is equal to 3 millimeters. And if you put that value in here, 2, 3, so now you are able to solve for F1 and F4, which is going to give you F1 is minus 100 U2, which is equal to minus 200 newtons. And for the F4, that is minus 100 U3, that is equal to minus 300 newtons. And for the finite element equation of the second element, let me write it here. We can say that second element, think about it, you have got a stiffness value of 200. So I am able to write, I'm just writing for that element. Because of that, just K2, 200 minus 200 and Ui, Uj, and just for this second element, the inlet force, initial Fi, the outlet Fj, and we can say I is equal to 2 j is equal to 3, the numbers of the node for the element 2. Thus we can calculate the spring force like F or Fj, which is equal to minus Fi, and I can write it as a row vector minus 200, 200. I can multiply it with U2 and U3. So that is 2 I have found here, and the other one is 3. I can say that we have got a known values, so it is easily to calculate it from there. F is equal to 200 newtons. Yes, let me extend our time. So after this equation or the example, let me give you another example for more complicated systems. Yes, we have got an example of parallel and serial connected spring system. Let me give it to you. Yes, this one. I want to give you the values, and we have got a arbitrarily numbered nodes. This is important. First element, second element, third element, and fourth element. But we have got the nodes. First node here. Look at here. This is the first node. Node 2. Node 3. And we have got node 5. And we have got node 4. So, if we write these, I will make it a little bit more faster to you. I'm just giving the results. And it means I'm going to give you the definitions. So, let me give you the stiffness matrices. You can easily make it by yourself also. These are the stiffness matrices. And for giving the stiffness matrices, we will going to put them together and create the matrix or assembled matrix for the global stiffness definition. Let me show you. Maybe I will take these a little bit higher. And after the superpositioning all of the matrices, we will get the stiffness matrix here. And this one is also symmetric matrix, banded, but this time it is singular, which means the determinant of the K matrix will be equal to 0. So for this week, the class is over. For the next week, we will try to continue maybe with another example and then jump into the new issue maybe. The class is over. See you on the next week.